Hello there. Happy Monday. I just saw your assignment on related rates. Good job. I'll take a look at that and post some solutions and stuff. But let's move on to a new topic, and that's finding maximums and minimums on a function using, of course, the derivative. So here's some pictures. A relative or local minimum is a point that's whose y coordinate is smaller than the y coordinates of the points that are locally close to it. So if you zoomed in on this value right here, 1, that's the lowest y coordinate on this little section of curve. Now you could also have absolute or global max-mins. An absolute or global max-mins, the global max is the point with the highest y-coordinate of all the y-coordinates, like that guy. That's a global max. It's not a local max because we don't know what's happening on the other side. So if you have endpoints, an endpoint could be a local max, a local min, a global max or a global min, or neither. So this point right here at x equals 2, you're including 2, that's a global or absolute max. This endpoint is neither. This point, 0, 1, at x equals 0, you have a local or relative min. Local and relative mean the same thing. And it's the absolute min. So a relative extreme could be also a global extreme. So at x equals 0, this function has a local and global minimum at x equals 0. It has a global max at x equals 2. There is no relative maximums. Don't include the endpoint. There is no absolute or global max, but there is a local and global minimum at x equals 0. Right? For some reason, if you had this guy like this was open, then it wouldn't be considered a minimum. Notice the points filled in there. So this would be a global max. And there would be, this function has no minimum whatsoever because mathematically you can get closer and closer and closer to the point x equals 0. And as you get closer and closer, the y coordinate is getting smaller and smaller and smaller. Okay? So no matter how close you wanted to get to the y coordinate 1, 1.01, 1.001, 1.00001, you can get closer. The y coordinate can get closer and closer and closer to 1. So there is no absolute or local minimum because there is no smallest y coordinate. Now if you look at this guy up here, there are no endpoints. Out there like that. There you go. So these go on. There's arrows at the end of these guys. So since this decreases without bound, there is no global min. And this increases without bound, so there is no highest y coordinate, so there is no global maximum. This point at x equals 2, you have the local minimum. You can also call it the relative minimum. And at x equals 0, you have the local maximum. That guy right there, relative max. Now you can also have relative max mins at corners. So here's like the absolute value function. That is a local or relative min. But at that corner, the derivative does not exist. Right? So when we're hunting for max and mins, we're going to have to also figure out where the corners are, as well as where the smooth peaks and valleys are. Where you have smooth peaks and valleys, you have horizontal tangent lines. Up here, there is no tangent line. So we have to look for both horizontal tangent lines and places where the derivative does not exist, where there is no tangent line. Okay, so here's the two situations. Okay. A peak at a corner or a valley, or a peak or valley at a horizontal tangent line. Where these two things occur, you have what is known as a critical value. Right? So the function is defined at C, so it's connected, it's continuous. If the derivative at that point equals 0, you know the slope of the tangent line is 0, which means you might have a max or a min. Okay? If the derivative does not exist, the function is not differentiable, okay, then C is a critical number. So when you have corners like this, the derivative undefined, or tangent lines with slope equal to 0, these values of x are called critical values. So what we're going to have to do in order to find max mins is find critical values. Now, you don't have to have a max or a min when you have a horizontal tangent line. You could also have this, something like that. You could come up, flatten out, and then continue to increase. So right there you have a flat spot on the curve. The tangent line goes through, okay, but the curve continued up after that. So this value of x, whatever it is, would be considered a critical value because the derivative is equal to 0, but that value does not produce a max or a min. So we have to be on the lookout for these three different situations. All right, so to go max min hunting, relative max min, here's the steps, here's the guidelines. Come on, get bigger. Too big. All right, so extrema, plural for extremes, relative max mins. Continuous, so the thing's connected, and you have a closed interval, so you have endpoints. If it, like a parabola goes on, the domain is all real numbers, that's fine too. Okay? Use the following steps. Find the critical values. So to find the critical values, we need to take the derivative, set it equal to 0, and then find also where it's undefined. Right? Then we're going to plug in each number, check the endpoints, and see which ones are max or mins. All right, so basically it comes down to finding the derivative, set it equal to 0, find where it's undefined, and use those values to determine if we have max or mins or not. Right? And to do that, we are going to make what is known as the first derivative table.